happening up there? We have a name for that type of reaction. What is that starting to look like it might end up at? As a hint, you might look to the lower section. So not only is it a nucleophilic addition, but it's the nucleophilic addition in the formation of not just a pi bond, an enamine. We're doing the exchange of our oxygen for our nitrogen. We did this already. Okay? That first step was our standard nucleophilic addition from the previous section. If we continue to propagate this mechanism through, we end up eventually reaching a stage that's shown in the bottom setup. What happened in that bottom setup? Well, we reform a pi bond. Formation of a pi bond is known as an elimination. What did we kick out in the formation of that pi bond? Water, which is a dehydration. Water specifically, though, is a nucleophile. What have we done? Nucleophilic elimination. Okay? So those reactions that we've looked at have already started to do this. Okay? The context that's going to now change is that instead of, that's not the right button, instead of looking at just a standard carbonyl, we're going to end up switching it to a carbonyl from, say, an aldehyde. Oops. Ketones. We've looked at all those reactions and we focus primarily on nucleophilic additions. We're now going to change that group to, say, a chloride. What's the difference between chloride and those other groups? So the carbonyl carbon becomes more electrophilic. What else is special about this chloride? It is a fantastic leaving group. Okay. So a very subtle change in our electrophile is now going to change what potential reactions come afterwards. So when our nucleophile reacts, we will end up with an intermediate just like we have in the uppercase, or in that example that I did not erase. We'll still end up with an intermediate like this. But in that case, what do we also have? We have the ability of a leaving group. If that leaving group then leaves the structure, I'd be left with what functional group? I know it's kind of a hard question because I didn't specify what the nuke is. We now potentially have a ketone, which can do what? React under nucleophilic addition reactions. So we can end up cycling this nucleophilic addition and elimination reaction right back into another nucleophilic addition reaction. All of that is going to depend on the strength of the nucleophile being used. Okay? So a lot of these next few chapters is really just repeating the same stuff you've already looked at. There'll be a few extra reagents that we throw in there because if we change the reactivity of our electrophile, we may want to stop that reaction at certain points. So we'll change the reagents to slow or prevent the reaction, just like we did with our oxidation for chromic acid and PCC. Right? So, take a minute, because we're coming back to or introducing more functional groups again. The acids and the esters are kind of your primary focus within this section. So you need to be able to at least name the acids. I'm actually going to have to double check again on deciding if esters are necessary to name or not. Okay. So we'll go through and take a look at a couple quick examples, trying to provide the name for each of these. So when you go through, of course, well, actually I'll give it to you guys. Which one should I attempt to name? First one. That's all I wanted to hear. First one. Upper left-hand corner is the one we're working on. I was dying for first one to come out of that. We go through, identify our longest carbon chain. Our longest carbon chain is how many carbons? 2, so we can reference this as F. Hybridization. Okay, this gets a little bit weird, but we're looking at primarily alkanes. The hybridization on that internal carbon is due to that last functional group, so we won't reference that. So we're looking at an And what functional group do we have? Carboxylic acid, and it becomes ethanoic acid. I've seen the O pop up sometimes, sometimes not. A lot of the times it seems to show up on making it sound better. If you said ethanic acid, it just sounds weird. Okay, so we throw in the extra vowel. Is it typically referred to as ethanoic acid? No. What is it typically referred to as? Acetic acid. So watch out for that common name popping up. You're not responsible for the common names, but there are some that do kind of sneak in there. Okay? Acetic acid is very, very common, no pun intended, as a reference on this. The other thing that you'll typically see is that that group is often referred to as acetyl, hence the term acetic acid, because the YL is really just what we would use in reference to a substituent. If it's not a substituent anymore, we would change that to the ending, and it becomes acetic acid. Where did that O disappear to? Well, acetoic acid just sounds weird. Okay? You guys want to try a couple on your own? Okay. Main chain. Okay. It can be very helpful to identify your main chain when you go through and look at your individual reactions. Okay. So in that upper right-hand corner, you'll notice that we're actually identifying the shorter carbon chain. Why are we identifying the shorter carbon chain? It contains our higher priority functional groups. Okay, so remember, we're always trying to identify those higher priority ones. We have the acid in there, so we would end up seeing probably another oic acid showing up. That is by definition going to be appearing at which position? 1, so we don't even need to worry about numbering it. Okay. The next part of this that's missing within there is the context of the hybridization of your carbons. Okay. You'll notice that we have an alkene floating through the middle of that. We need to specify that by dropping in our ene. Because we have two functional groups, we need to make sure that our numbering does not get confused between those. So we'll have to drop in some numbers in front of the ene, and that ene would be at position 2. So we have but 2 ene, and if we wanted to get fancy on it, we could call it 1 oic acid. Okay. Is that the only thing in here? We also have an aldehyde. Sorry, I meant to go with a different color. How do we name the aldehyde? So 2 things came out, an al and an oxo. We'll put in the dash in reference to where they're used. When do we use the al? At the very end, because it's the highest priority functional group. Is an aldehyde the highest priority functional group here? No, the acid is. So we end up using the oxo. So we can get away with using that as a suffix. Okay. Where did the oxo show up? Not at the beginning, actually at the end. Showed up at 4. Oh, I see what you're saying with beginning. We would have our 4 oxo. And the last piece, oh darn it. And we have our propyl, which shows up at which position? Position 2. So we have a 2-propyl butene 1-oic acid. Why does the propyl come after the oxo? Alphabetical order. Okay. Lovely name. Is there anything more we could be adding to this? Not RNS, but right idea. E and Z. Cis and trans really only applies to looking at 2 groups. This officially has 3 groups. Cis and trans is not the best usage of terminology. You need to be using E and Z. We'd have to assign our higher priority, our highest priority groups. Sorry, I'm going to have to erase all that color. Oh, that was the wrong eraser. Let's try that. Around our double bond, our highest priority group it would star. Where are those stars relative to our double bond? Same side, or as Jimmy's referencing here, it's on the same side, which means we are looking at Z. Typically, your Z, EZ nomenclature gets shifted to the very front of the name. We have to specify where that Z showed up. Where did it show up? Position 2. So we'd have 2Z, 4-oxo, 2-propyl butene, 1-oic acid. Lovely.
Why is the bute?
Okay. Why is the
Bute?
why is it bute in general?
Why is it after the propyl?
The bute is the main chain.
Yeah.
So that's why it's coming after the propyl. Your main chain, it's not a substituent. It is at the end. Everything else are the functional groups on the main chain. This is an ene, which is a functional group on the bute. The oic acid is a functional group on the bute. These two are substituents. So our substituents gets listed out front. Our functional groups get listed at the end. The bottom two both get named kind of as esters. So we can go through with our IUPAC terminology. We have an ethan, because this is what functional group? An ester. What we'll do is name that piece in blue 08. We have an ethanoate functional group. And on that ethanoate functional group, what do we have? An ethyl substituent. So we have ethyl ethanoate. Also commonly referred to as what is the piece in blue? Right there. An acetyl, ethyl, ethyl acetate. Okay. You're still seeing some of that direct translation across with your ester name. You'll notice that that O again floats in there. Okay. Sometimes showing up, sometimes not. I'm sure there's an English explanation for why. Last one. 1, 2, 3, 4 carbons. So we have a bute. All of those are sp3 hybridized. So we have a butane. What functional group are we looking at? This is kind of weird, isn't it? What's an ester? How would I make this an ester?
There's some R group attached to
That K needs to be a C. So it's not really an ester. Okay. How about an acid? Well, it's definitely not an acid because K is most certainly not H. This actually gets named as if it's an ester. So this should become butan 08. What is the substituent on our butanoate ester? Potassium. So we have potassium butanoate. Okay. Remember, you're responsible for your nomenclature. Go back, review it, be aware of it. It does show up, though to a much lesser extent. Okay.
So once you put that in solution and
As soon as we drop potassium butanoate into solution, what happens? It's going to completely ionize because it's an ionic bond. So as soon as we drop that into a water solution, yes, it should ionize. And then you would have the carboxylate. You'd have the conjugate base of the acid and the potassium ion free floating separately from each other. Other questions? These are up here not so much because I want you to name them, but more because I want you to be aware of some of the kind of nomenclature extras that pop up in here. Come on, pen. How might we go through and name that compound? How many carbons? Why 2? Yes, there's 3 carbons, but why are you only saying 2? 2 in the longest carbon chain. That other one is a substituent on our process. So we could go with an ethan. What's the functional group? It's an amide functional group. You are responsible for recognizing amide functional groups. Don't think you're going to be really responsible for naming them. Okay? So, believe it or not, the name actually isn't too bad. How can we refer to this as an amide? Yup, as an amide. It's ethanamide, really creative. Okay, so that's not too bad. But if we just say ethanamide, does that take into consideration that extra methyl? No. And in fact, if we look at its counterpart across the screen, we would get also the exact same name if we don't consider that methyl. So we'd have ethanamide for both of those. So we need to come up with some way to reference that methyl group. So maybe I just write methyl ethanamide. You're shaking your head? No, I like that. Why is that bad? Interesting idea. When we go over to the other side, you might say it's the same thing, but I can make a real quick change and say it's now dimethyl ethanamide. The YL means it is a substituent. Where do our substituents exist? On the main chain. Is that methyl on the main chain? No. And if we left it as this kind of reference, it's an implied that we're putting that methyl at the 1 position. And if we put it at the 1 position, is it ethanamide? No, it would be propanamide. All we did was shift the methyl group to the other side. So we need to reference where the methyl group is. Well, could I label it as being at position 1 or position 2?
No,
Why not?
because it's on.
The 1 and the 2 are carbons. So how about position 3? Okay. There is no 3 position. Remember, our numbering is according to the carbons. It's not attached to a carbon. So how can I reference that that methyl group is attached to a nitrogen and not a carbon? N-methyl ethanamide. How do you reference it on the other one? Why do you have to say NN? You have to specify the location of every single substituent. Okay? We've run into this before. If you have 2 methyl groups at the same location, you still have to say that location twice. So it becomes NN dimethyl. Okay? Yes, good call. NBS. And I just started failing to draw that, so let me try that again. If we looked at NBS, this was succinamide. I think there's a double bond there. Succinamide. NBS is N-bromosuccinamide, meaning attached to the nitrogen, I have a bromine. Okay, so we have seen that terminology pop up before. Just as a random question, what is NBS used for? It is a radical reaction with bromine. What type of radical reaction? Unfortunately, it can be used for addition, but that should not be your primary focus. I know that's how we used it in the lab. That's not your primary focus. Substitution. Okay, that's what we used NBS for, to give a very low concentration of bromine, which is why it's typically not used for addition, because the bromine concentration is too low. And we end up getting a substitution for a hydrogen at the most substituted position. Okay? Will you ever see those 2 compounds referenced as N-methyl ethanamide? That's why I love nomenclature. No. They very typically get referred to instead as N-methyl Right idea, but acetate does not take into consideration that it's an amide. Acetamide. Okay. The other one would be N,N-dimethylacetamide. Bottom one, I'm not even going to ask. What's the? I just started to ask it. What's the name of the compound on our left? So vinegar, way to go, super common on it. Vinegar, acetic acid, ethanoic acid. Okay. Next one over. No. Glacial, what does glacial mean when we talk about glacial acetic acid? Glacial just means ridiculously concentrated. The only thing that's present in that solution is acetic acid. Okay. So this is not acetic acid because it's not an acid, number one.
It's an acid anhydride.
That is typically referred to as an anhydride. Okay. You'll almost always, well, very rarely actually, you'll also sometimes hear it referred to as an acid anhydride because what is that piece in blue coming from? An acid. Okay. So you'll sometimes hear it referred to as an acid anhydride. In this case, it's referred to as, by its common name, acetic anhydride. Okay. Again, not responsible for the naming of it. I just want you to be aware of it popping up. Go back, look at the nomenclature rules if you have to when it comes to the homework. Questions? Okay. Yay, spectroscopy. Don't worry, really fast. IR spectroscopy. When we're looking at carboxylic acid functional groups, you need to be making sure that you make reference to the bonds present in a carboxylic acid when we're looking at the IR, not that it's an acid. What is this broad signal due to? It's due to an OH, not an alcohol, not a carboxylic acid. It's due to an OH, okay, or a hydroxy bond. That is it. Okay. Why is it not an acid? If I draw out a carboxylic acid, does it have an OH? Yes, it also has this carbon-oxygen double bond, and it also has this carbon-oxygen single bond. Do those bonds show up at that wave number and that shape? No. Okay. So when you look at the spectra, you need to be referencing the bond that's present. In this case, it's an OH bond. As we continue to process the spectrum, you should notice that we also have this big, broad, intense peak centering about 1700, which happens to be a C double bond O. I now have an IR that has a compound with an OH and a carbon-oxygen double bond. Is there a functional group that could potentially combine those two? Yes. Now you can say you've got a carboxylic acid. Okay. So it's being very careful in the frame of reference on how you're putting these together. That top example is probably the cleanest example you will ever see of a carboxylic acid. More commonly, if we look at the bottom examples, that's what you end up seeing. You get this kind of broad, messy nastiness. Okay. And in the other one, it's even worse. It's so broad and weak almost that it kind of just disappears and it just makes the CH stretches look ugly. Okay. So if you see a spectrum that potentially has all this nice flat baseline and then all of a sudden starts to slide on you, that slide might be due to a carboxylic acid being in your compound, which is due to the OH bond causing that thing to slide out and make a big mess.
So it's not necessarily going to show an OH peak.
You may not, and so you will not see the peak for an OH at 3300. That is a very interesting point. Why is the peak at 3300 non-existent? Why is it shifted? what happens to the wave number for a peak or a bond as that bond weakens? It shifts to lower and lower and lower frequencies. You can look at the carbon-oxygen double bond, your aldehydes and ketones versus, say, your esters, amides, acids, all of those. They end up shifting lower and lower and lower. Why? Because of that resonance that's weakening the bond. In this case, we're not looking at a resonance effect weakening the bond. That OH bond is already very, very weak because it's an acid. Its whole goal is to dump that hydrogen. Okay? Questions on any of that? HNMR, you might see the hydrogen show up in your HNMR. It'll show up somewhere in that 12 range, 12 to 14. It's usually very rare to see that show up. Why is it rare to see it show up? It is so acidic that is the hydrogen attached to the structure anymore? No. Well, if it's not attached, can we see a signal for something that's attached? No. Okay. More often than not, what ends up happening is that you just see this kind of flat section through that region. But if you zoom in on that part of the spectrum, you end up seeing, whoops, that was not the button I meant to push. You end up seeing a slight rise in a signal and a fall. It's just very difficult to discern from the background noise. Okay? Carbon NMR, not quite as important. Why might it not be as important for a carboxylic acid? Primary reactivity of a carboxylic acid is acid, which is based on what atom?
Hydrogen.
Hydrogen. Does carbon NMR look at hydrogen? No. Okay. So it's not as particularly relevant. You do see the carbon-oxygen double bond show up. It is also shifted to much lower numbers. Why is it shifted lower? What was that? It's weakening that double bond. Why is the double bond getting weakened? Because there's resonance from the other oxygen weakening the double bond, which causes your signal to drift lower and lower. So you end up seeing the carbon-oxygen double bond peak show up a little bit lower than 200. In this case, we're seeing it settle in about 180. Okay? Questions? Bronsted-Lowry acid is a proton donor. Bronsted-Lowry bases are proton acceptors. This is going to become super relevant within this section of material. Because what are carboxylic acids going to do as soon as they are formed? Donate a proton. Okay. What if we happen to have something in solution, say like a nucleophile? What's the issue with our nucleophiles? They'll act as bases. So as soon as we run the reaction once, we produce a highly acidic compound, which does what to the nucleophile? Weakens it to the point that what happens to the reaction? It doesn't happen. Okay? So in a lot of both this chapter and the next, you're going to have to be aware of these acid-base balances going back and forth, because you can produce a product that is now acidic that destroys the reaction from progressing forwards. So how could we ensure that the reaction does progress forwards?
Identify what's
Not too bad of an idea. Yes, we want to identify what's acidic. If your product is acidic, what can we do to make sure that it doesn't neutralize the nucleophile? Add a base. Okay. Make sure you have more base present to ensure that your reaction can continue to turn over. The two primary ones you're going to be concerned about are your carboxylic acid functional groups and amines. Carboxylic acids act as acids, and amines act as bases. We've already seen in the smart work a question with amines popping up where you had to protonate it. Why did you have to protonate it? Because there was an acid somewhere in solution, which meant that your answer is wrong if you don't show it protonated. Okay. I will freely admit this section is extremely dicey when it comes to the homework, because depending on what they're asking for, they may want you to provide it in the protonated state, they may not. So be careful with the questions that get popped up. If you start suspecting that that's an issue, send me an email right away. Say, hey, am I just missing that I forgot to protonate this? Okay? I can't help you if you don't ask. Okay? So be aware of it. It's a big, big issue through here. When we're looking at acid-base reactions, the only thing that's happening in an acid-base reaction is the transfer of a hydrogen ion. So if we look at these two reactions, top and bottom, which one is the acid-base reaction? Top or bottom? Remember, your acid-base reactions, the only thing that changes is the transfer of a hydrogen ion. It is only the top reaction as an acid-base reaction. The bottom one does show the transfer of a hydrogen ion, but at the same time it also shows the addition of the iodine as well. Okay? So be careful when you look at your reaction, make sure you're classifying it appropriately for the reaction being shown. It's important to be able to rank your acids and bases. We've got all of these rules which you've seen again and again and again. On deciding if you have a stronger acid, it's stealing electrons from hydrogen. Okay? We've got size effects, electronegativity effects, resonance effects, inductive effects. When we switch over to bases, you'll notice that what do we have? Size effects, electronegativity effects, resonance effects, inductive effects. The exact same things. Oh my gosh, that must mean the rules suck. Okay? What's happening as we switch from acids and bases? The definition changes, so the context of what makes a stronger acid or base will also change. Make sure that you're using the rules appropriately according to the definition of what you are trying to solve for. Okay? So, if we were asked to rank acidity for these, those first two, which is the stronger acid? The carboxylic what? Acid. Which is a stronger acid? The acid or the amide? You tell me. Okay, acid. So now the question, why? Okay. So I've already heard a couple answers float out there. One was resonance. Resonance is not going to be a good option to be looking at. Why? They both have resonance. Why, more importantly, is it not an important thing to look at? Resonance is third on our list for priorities on trying to figure out acid and base strength. So don't start there. Start with size and electronegativity. When we go through and evaluate based on size, we're looking at oxygen versus nitrogen. Within a row, what did we say happens to size? No change, which means same size, no size effect. So move to the next step. The next rule is electronegativity. Which one's more electronegative? Oxygen, which means what is it doing to the electrons in the bond with the hydrogen? It's holding them even tighter, which means stronger acid. Next one. Identify your strongest acid in each of these. Hopefully you can recognize it's these hydrogens. Size. What atoms are we comparing size on? Oxygen versus. Okay. So no size difference. How about electronegativity? Same. Resonance. Which leaves us with inductive effects. We're looking at fluorine doing what? Pulling the electron density away from those atoms, which means it pulls electrons, pulls electrons, pulls electrons. The electrons that were in the bond between the oxygen and the hydrogen are now being pulled where? into the structure, which means are the electrons available to hold on to the hydrogen anymore? Which means the hydrogen is now gone. The species acted as an acid. Very, very acidic. So which of those is the most acidic? Far right, followed by? I don't know why I'm writing left there. Let's go with next. And then least. Last two. What are you suggesting? Why? So it is closer, so you're suggesting an inductive effect. Before you get into inductive effects, what should you be looking at? You should be looking at sizes. Okay. Same. Electronegativity, same. Resonance. How does that group affect the other structure, or our acid functional group? What would we need to do? Draw resonance structures. If we look at how charge shifts around the ring, why does that help us?
Because the electrons will be drawn towards the positive charge.
Our electrons are going to be drawn into the structure to support a positive charge. Okay? We can use resonance to help us predict what's happening within these. Okay? Which one of these structures has the least electron density to stabilize that OH bond? The one on the right, which means more acidic. Evaluate your resonance. Okay? Questions? Okay. Last fun thing on acids and bases. What happens to a structure that has multiple acidic functionalities and we change the pH? How many of you have to move into biochemistry? Guess what? This is right up your alley. Lucky you. Okay. What happens to this structure as I change the pH? Let's say the pH, whoops. Oh, I lost connection. Say the pH is very low. What does that mean? The pH is 1. What does that mean? It's super acidic. What happens to the structure? Shaking your head, no, I don't quite know what that means, but I think I know where you're going. What do you mean? What would it be equilibrium with? That are attached to the structure. What we're looking at, whoops, let's not draw resonance. Is the balance between these two species. If we're at a pH of 1, where should our equilibrium lie? Towards our acid form or our carboxylate form? Towards the acid form. What happens if I change the pH? Make it pH 7. I'm now going to shift towards the carboxylate form. How about I make it pH 4.2? Anybody know the pKa of a carboxylic acid? It's right about 4.2. If the pH is exactly at that pKa value, what happens? You are in equilibrium. We have an equal concentration of the protonated form and the deprotonated form. Right? So it's all relative, looking at your pKa versus the pH in predicting protonation states. This case, not that big of a deal. What happens if I make it more complex? What's the issue now? What did I add? I've got a base on one side and an acid on the other. Right? How is that going to change how this structure reacts? Let's take it to a nice easy pH. By easy, it's not really easy, but let's just say it's easy. pH equals 7. What should happen? It's tricky. pH 7, what should happen to the acid?
Depend on whether your acid is stronger than your base on the structure.
Believe it or not, no. If you are at a pH 7, what happens to the carboxylic acid? We are at a pH that is more basic than the functional group. So what do we do to that hydrogen? Remove it. We also have to evaluate the other half of the molecule. How do amines act? As bases. We are at a pH that is what? More acidic or more basic than a base? More acidic, which means what should happen to our basic functional group? It should become protonated. I can separate the two functional groups and evaluate what pH I'm at relatively to decide the different protonation states. Okay. If we're under strongly acidic conditions, we're looking at a pH of maybe 1. What's going to happen to the protonation states? If I'm at a strongly acidic environment, what should happen to my base functional group? It should be protonated. It's got it. If I'm at a strongly acidic environment, what should happen to my carboxylic acid functional group? It should also be protonated. Okay. So it's evaluating the relationship between your pH and your pKa. That relationship is ultimately coming from what famous named equation? Not Le Chatelier. Henderson-Hasselbalch equation. Yeah, lucky you. Okay. One little cheat you can do, if the pKa is lower than the pH, yes, then you can remove the hydrogen. Okay. We're saying that our functional group is more acidic than the environment we're in. If the pKa is higher than the pH, okay, we are saying we're in a more basic environment, so we want to keep, I always get this backwards. I hate having to memorize rules because I always screw them up. pKa is lower than the pH, then remove the hydrogen. pKa, pH. Stupid rules. Let's pick some numbers. pKa is 4.2. pH is, let's do it this way. 4.2 pKa, pH 7. The pH is, I had to switch it with that pKa system. Which one are we looking at? I need your help. That one? It's higher. No, it's the other way. Our pKa is in a more acidic or in a more basic environment, which means we need to remove the hydrogen. Okay. If we switch this up to the pKa of our amine, so we jump up to say a 9. Same pH, what should happen? Now the pKa is higher than the pH, so my pH is more acidic than my pKa. What does that mean has to happen? I have to be in the protonated state. Keep your hydrogen on. Okay. Little handy-dandy rules are handy-dandy if you can keep them straight in your head. I could never keep that straight in my head and I always have to drive it. Okay? Questions? This becomes super important when we look at how different functional groups, and in particular amino acids, react. Name of this function or amino acid? I think I got that as aspartic acid. Okay. What's the issue with this functional group or this amino acid? It has 3 sites of acid-base characteristics, which means when we change the pH, what happens? All 3 of those sites potentially change their protonation states. You are responsible for, in biochem, or deciding what that charge state is. Those of you taking a PCAT, it's massive all over the PCATs. Okay? And I've seen it a lot in pharmacy school. I've had a couple students come back and ask about it. Okay? You will see it pop up again in biochem. So, polar pi bond, all the way back to the reactions that we should be excited about. Polar pi bond with a leaving group attached. What happens? Our nucleophile comes in, attacks our electrophile. We need to then break a bond because that carbon has too many bonds. What bond should we break? Why the pi bond and not the bond to the leaving group?
Because it's higher in energy.
The pi bond is higher in energy than the sigma bond. We should break the pi bond first. This forms this special intermediate. This intermediate carries a very particular name. What is different about it in comparison to either the product or the reactant? Yes, it's charged. Keep going. What else is different?
It has a chiral atom.
Potentially chiral atom. What's special about that atom? For it to be chiral, what has to be? How many things have to be attached to it? 4 things, which means the shape is tetrahedral. If we look at that same carbon in either the reactant or the product, do we have tetrahedral shape? Guess what this intermediate is referred to as? The tetrahedral intermediate. Okay? It's the clutch intermediate in all of these types of reactions. Okay? Why is it so clutch? Take a look at that reactant or that intermediate. Is it stable? No, what's wrong with it? It's charged. So what should we do? Stabilize that charge. How can we stabilize that charge? We need to bring in a positive somehow. If we bring in a positive from outside the structure, number one, very rare to find a reasonably positive charged species outside the structure. But number two, our larger issue is that we very commonly now have 3 very electron withdrawing groups attached to the carbon. That carbon is now a little bit peeved. Okay? There's too many groups pulling electron density away. It needs to stabilize. Okay? So yes, that oxygen needs to find something to donate its electrons to. That carbon at this instant is also saying, give me electrons. So what does the oxygen do? Instead of finding a source outside the structure, it goes within the structure and reforms the pi bond. The issue with reforming the pi bond is we now have too many bonds. So what do we have to do? Break a bond. What bond do we break? Okay. With the way our mechanism is drawn, we're breaking off the leaving group. And we'd have a leaving group come off with a negative charge. What's going to decide which way this reaction goes, if it favors the reactants or the products? Stability of the leaving group in comparison to what? The nucleophile. Okay. You all theoretically wrote down or took pictures of that quiz. If you didn't, talk to some people in the class. A few people did. Okay. Evaluate. What is your nucleophile? What is your leaving group? Should that reaction have occurred? Okay. Do not lose bonds. I noticed a lot of people doing that too. All of a sudden, bonds were either appearing or disappearing, kind of at will. This is your basic mechanism that applies to everything in the rest of these chapters. Okay. What conditions did we run this reaction under? Negative charges are floating all through this, so more than likely we're running under basic conditions. Yes, most of these reactions are run under basic conditions or neutral. Okay. We could change them to become acidic. Okay. The very first step of an acidic mechanism would be to do what? We protonate the oxygen. Why does that help us? Our electrophile becomes more electrophilic because that bond is now fuller. I'm not sure what I was trying to say. Is more electrophilic, let's just say that. Okay. More fully positive? I don't know. Okay. That's going to help polarize so that our nucleophile can come in and attack. If we add a strong acid, can we use the nucleophile as shown?
No,
Why not?
because it's a negative charge.
The negative charge, the nucleophile would very likely make it act as a base. It would react with the hydrogen, so we would not see this mechanism run as shown. We'd have to neutralize those charges first. Okay. What are our possible structures that have, or possible leaving groups, not leaving groups, possible electrophiles that have leaving groups? We've seen some carbonyl structures already. Ketones, aldehydes. Would these be expected to go through a nucleophilic addition and elimination? Why not? CH3 and hydrogen cannot stabilize that electron density. So these will not go under nucleophilic addition followed by an elimination. What do those groups need to be? Yes, a good leaving group, fair enough. What characteristics would make that a good leaving group? Bromine, good choice. All of our halogens, technically halides, would be good options. Why? They're large and they're electronegative. Both of them, both characteristics of things that can stabilize that negative charge. Other options? Oxygen. Why would oxygen help out? Electronegative. We can potentially even do our nitrides. Why are nitrides questionable? Less electronegative. They do not stabilize the negative charge very well. We've got a... Sorry, what was that? If we had water in there, we're looking at an oxide. So here's a list of potential functional groups. We're officially done. You'll notice that what is in common between all of these? In each case, we're looking at an electronegative element attached to a carbonyl. You'll also notice that I've got them in kind of an interesting order. This bottom one, not very reactive to a nucleophilic addition and elimination. Why? I'd have O-2. Not a very good option. Next one up, better or worse? Better because it would only leave as a -1 as opposed to a -2. Next one up. -1 on an oxygen. Is that better than a nitrogen? Yep. Next one up.
-1, but there's resonance.
There's resonance in the next one up. Last one. Really good leaving groups. Each of these cases, we are changing that atom, which changes the leaving group ability, which is then going to change something to do with its reactivity. Okay.